To find all the cosets of the subgroup generated by 4 on the group Z12, we can start by identifying the number of possible cosets that is true for both left and right cosets. We can determine the number of left cosets of a certain subgroup, in this case, a subgroup generated by 4 on Z12, if we're going to use their what do you call this one, the indices, or their the index of the said subgroup in our given group Z12. Let's start by giving here or writing here our groups and our given subgroup generated by 4. So we have Z12. We know that Z12 is the addition modulo 12. So we're taking all the remainders of certain integers when divided by 12. So if we have here 0, that means it divides entirely all the integers by 12, hence there's no remainder. The next is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We don't have 12 because when we divide 12 by 12, it has no remainder, hence we already have 0 here. Now for our subgroup generated by 4, okay, so we're going to list here all possible remainders of when we generate a 4. We use 4 as our generator for all integers, and then divide by we will be getting the remainder when divided by 12, because that's addition modulo 12 as well. So we have 4, right? 4 plus 4 is 8. 8 plus 4 is 12, but 12 is divisible by 12, so we have the remainder 0. If you have 0 plus 4, we'll just return to the first element. Hence, this is the subgroup of Z12 generated by 4. We have 0, 4, and 8. Or you can rearrange it as 0, 8, and 4. It's up to you because it's a set. Now, let's consider this as our H. Okay? Because, and this would be our G, or our group, because we can determine now the number of left and right cosets by solving here the index of H in G, represented by this notation here. This actually means that we just simply need to take the order of each group, and by a theorem of Lagrange, that means we can it's what do you call this one, the index or the order of our subgroup is divisible by the order the order of the group is divisible by the order of our subgroup. So for our Z12, okay, over our H here, so we have here 12 because we have 12 elements, divided by our H, we have 4, 0, for the H, which is the subgroup generated by 4, we have 3. So we are expecting here 4. This actually tells us the number of cosets for both right and left cosets. So there should be 4 left cosets and 4 right cosets. Okay, that's our hint already. Now let's proceed with our left cosets. For our left cosets, it should undergo this pattern. If we have here A times a certain group, which is in this case our H here, or the subgroup generated by 4, is this just equal to AH for all small letter h element of our subgroup H for all A element of our G or Z12. This would mean that we are going to operate all elements of our G, our Z12, with all elements of our H. Whatever be the result, that's actually the coset, the first coset. So we're going to try all elements of our Z12. Take note that we have 12 elements, but why is it that there are only 4 cosets? So we're going to check it here as we move forward. And take note that our operation is Z12, or our group is actually on Z12. That would mean that we're talking about addition modulo 8. So the first element of our Z12 is 0. So we're going to have 0 plus H, but this plus is addition modulo 12. Okay? That would mean we will be adding 0 to all our elements of our H. Let me rewrite H in this manner. 0, 4, 8. as mentioned, since it's a set, so we can rearrange the elements. And let's just arrange it in that manner so that we can compare all the results later. So 0 plus 0, 0. 0 plus 4, 4. 0 plus 8, 8. This is the first left coset of the subgroup generated by 4 on Z12. Okay, that's the first. The second is if we're going to use the second element of our Z12, 1. Again, this is still addition modulo 12. So if I may forget placing this the next few operations later, it automatically means on Z12. So please be guided with that. Nevertheless, so 1 plus all the elements here. 1 plus 0 is 1. 1 plus 4 is 5. 1 plus 8 is 9. Okay, that's the second left coset. We are told by this computation there are 4. So we're almost there. The next is if we're going to use 2 plus h. So again, I might not be writing 12 here, but it automatically means like that because we are on the same group of Z12. So that means 2 plus 0 is 2, 2 plus 4 is 6, 2 plus 8 is actually 10. This is our third left coset. For our fourth left coset, we have 3 plus h. So 3 plus 0 is a 3, 3 plus 4 is 7, 3 plus 8 is 11. Okay, so we already have 4. So there should be 4. Why is it that we still have other elements that we haven't tried? Let's try to check. If we are going to use here 4 as the next element here on our Z12, 4 plus h, it will look like this. 4 plus 0 is 4. 4 plus 4 is 8. 4 plus 8 is 12. That's 0 modulo 12. Okay? Look at this one here and compare it to this first left coset. Take note, there are sets. So we can just simply rearrange the elements. 0 plus h as our first left coset and the fifth left coset here, 4 plus h, have the same, or are actually the same sets. So they are just counted once. This would mean that 0 plus h is just the same as 4 plus h, which is also true if we have here 8 plus h. Because if we have 8 plus h, let me use a color here, black. Okay. If we have 8 plus h, so 8 plus 0 is 8. 8 plus 4 is 12. That's 0 modulo 12. And 8 plus 4. Yeah. 8 plus 8 is 16. That's actually 4 modulo 12. So it's still the same. That is why we only have 4. Because even if we haven't tried the rest, they will just be returning to the same given. Look at this here. This is also true with actually 5 plus h and 9 plus h. Because for 5 plus h, 5 plus 0 is 5. 5 plus 8 is 13. That's 5 plus 4 is 9. 5 plus 8 is 13. That's 1 modulo 12. They are just the same. As for 9, 9 plus 0 is 9. 9 plus 4 is 13. That's 1 modulo 12. And 9 plus 8 is 17. That's actually 5 modulo 12. So they're just the same. So this is actually entirely true. There are only 4 cosets. Specifically here, 4 left cosets. These are also similar to their respective continued cosets. Like for 2, that's 6 and 10 plus h. For 3 here, this is also same as 7 plus h and 11 plus h. So as mentioned here, there are 4 left cosets for this given subgroup generated by 4 on Z12. Now, this is still left cosets, so we are not yet done. Let's proceed to the right cosets. To the right cosets, it follows the same concern, and we are sure that there should only be 4. Okay, but the notation would be like this: HA, which is just the result when we operate all elements of H, and that A for H, all elements of our subgroup H. And of course, our A would be element of our G, which is Z12. So if we're going to use here the first element of our H, take note, this is our H, right? I mean our G, this is our H. Or we can rearrange this. So let me just copy it here. H is 0, 4, 8. And our Z12 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So the first right coset is h plus 0. Again, that's modulo 12. So this is our h. So 0 plus 0 is 0. 4 plus 0 is 4. 8 plus 0 is 8. Okay. And if we're going to have plus 1, again, modulo 12 as well. So we have 0 plus 1 is 1. 4 plus 1 is 5. You have 8 plus 1 is actually, 9. That's our second right coset. If you're going to examine just for this first two, it's just actually the same as the first two left cosets. 048, 159, 048, 159. How did this happen? This because our operation on Z12 is actually addition modulo 12, and it's actually commutative by nature. It's an abelian group. If we have an abelian group, aside from the number of left and right cosets to be equal, the left and right cosets are also identically the same. Okay? Because if we would like to continue this to 2, 0 plus 2 is 2, 4 plus 2 is 6, 8 plus 2 is 10, and if we have here plus 3, we have 0 plus 3 is a 3, 4 plus 3 is 7, 8 plus 3 is 11. As you can see, these are also the same as the first, okay? This is also the same as the third and the fourth left cosets. So we can see here, because our group is an abelian group, is abelian, or there is the concept of commutativity, the left and the right cosets are just the same. And of course, we also have 4 right cosets as already determined earlier using the index of h and g. So we also have here 4 left cosets. So this is how we illustrate the cosets of this certain subgroup generated by 4 on Z12. We're able to identify the number of cosets, the expressions of those cosets, and the relationship of the left and the right cosets, because our group is an abelian. But if it's not abelian, that means that our left and right cosets may not be the same, and that the only thing that is the same for both of them is the number of cosets indicated by this formula. Of course, if you're going to continue this, just like earlier, if you have h plus 4, this will just return to this first here. Okay, same as earlier. 4 plus 0 is 4, 8 plus 0 is 8. We have 8 plus 0, 4 plus 0, 4 plus 0, 0 is 4. 4 plus 4 is 8. 8 plus 4 is 12. That's 0 modulo 12. So we still have the same result, and together with the rest of the examples as well. So again, this is how we show or find the all cosets, because you're asked here about all cosets. The next few videos will talk about specific cosets, whether right or left. It will now be dependent on the type of the subgroup or H that we will be given, together with the group given. Thank you very much for watching.